Okay, so let's solve the first order IVP. Y prime minus x sine x is equal to 0, subject to y of 0 is equal to 4. And I just kind of wanted to give a different integration scheme in this problem. So let's go ahead and write the y prime as dy by dx. And then I'll transpose the x sine x. And upon multiplying by dx, my first order ODE is fully separated and I'm ready to integrate. So let's go ahead and integrate both sides, and the left hand side is still pretty simple. So I just have my function y of x, so I don't have to do anything fancy, any fancy algebra after this. And then now I just have to integrate x sine x, and this brings up integration by parts. And I'll probably produce a Cal 2 video where I guess I could show from the product rule how integration by parts actually comes about. But it's pretty simple, and I guess most of my students just remember that the integral of u dv equals uv minus the integral of v du for some functions u and v, which are both functions of x, say. And if we compare that to what we have here, I would probably choose the x to let that equal to u, and then the sine of x dx to equal to my dv. Just because if I look at this integral, I look at the integrand, it should be clear that by choosing u to equal x, when I take du, I'll just get dx. So it doesn't introduce any more complexity, I guess, into the integral itself. And v should, it's just going to flip-flop from sine to cosine. So if I would have chosen u equal to the sine of x, the du would have a cosine in it, and then I guess if I keep doing that, I'll never sort of get out of this integration by parts. So by doing this, I'll get du, in this case, is equal to just dx, like I said. And if dv is equal to sine x dx, then v, which is going to be the integral of the sine of x, should be a negative cosine of x. Okay, so if I put this all together, I have u, the integral of u dv, the integral of u, which is x, and dv is sine x dx, should give me uv. So I'll get x, v is minus cosine x minus the integral of v du. So I get a minus cosine of x, and du is just dx. So you can see that I didn't introduce any added complexity when I did the du. So if I go ahead and I have a minus and a minus sign here, so I could write this as a minus x cosine x plus the integral of the cosine of x dx, which just gives me a minus x cosine of x. And if I integrate the cosine, it brings me back to the sine. Well, the antiderivative of the cosine is the sine, so I get plus sine x plus some arbitrary value c, some arbitrary constant. So the function that I seek as the solution to this ODE is minus x cosine x plus sine x plus c. But this is a single parameter family of curves because this value c, of course, shifts up the plot of minus x cosine x plus sine x. And there really are an infinite number of solutions. It only gains uniqueness if it passes through y of 0 is equal to 4. So that brings about that whole existence and uniqueness thing. Okay, so let's go ahead and apply this initial condition, and we'll get 4 equals, so if x is 0, I get a minus 0 times the cosine of 0. So it's like 0 times 1, I'll just get 0, plus the sine of 0, plus c. And all this just says really is that c is equal to 4. So now I have the unique solution. Y of x equals negative x cosine of x plus the sine of x plus 4.